Good morning, friends. Today we are going to discuss the next part of the unit 1 of the paper 1. Today we are going to discuss the standard state. Here the MCQ will be there based on this standard state. The standard state of a pure element or the compound is a more stable form of the pure substance at the pressure of 1 atm, 1 atmosphere. It is 1 atmosphere is nothing but 10132.5 Pascal. Yeah, you can take 10, that is a 10132.5 Pascal at 25 degrees centigrade, means at the 298 Kelvin. When the reactants as a product are in their standard states, the word standard italic is placed before the term in which it applicable. Example, enthalpy of reaction in standard state can be written as delta H minus, or say delta H 0. Gaseous at 1 atm for then liquid these are the standard state. 1 atm for the water, liquid 1 atm for this particular water, ethanol, bromine and mercury, and all metals, they will be in the standard state at the 1 atmospheric pressure. Crystalline state for the NaCl, urea, dextran, etc. These are the examples. The standard enthalpy of the formation, delta HF0 or say delta HF minus. It is increasing the enthalpy when 1 mole of the compound in its standard state is formed from its element in standard state. Very simple it is again. What is there? The here the MCQ is also based. Standard enthalpy of formation is the increase in when 1 mole of the compound in its standard state is formed from its element in the standard state, or it is the increase in the enthalpy when the 1 mole of the compound in its standard state is formed from its elements in the standard state. This is standard enthalpy of the formation. In the standard enthalpy of combustion, it is denoted by the delta SC0 or say delta SC minus. It is an increase in the enthalpy when the 1 mole of the substance is completely burnt, B-U-R-N-T, burnt in oxygen gas in standard state to give the product in their standard state. Combustion means it should be the burnt. Okay, and enthalpy of the formation, there should be formation of the compound. Okay, both example is given here. Carbon graphite plus oxygen gives you the twice CO2. Delta HF0 for the CO2 at 298 Kelvin is a minus 398.5 kilojoule. Whereas delta SC0 for CO2 at 298 Kelvin, opposite reaction will be there. Twice CO2 will get combust into the carbon graphite and oxygen. It has the enthalpy of the delta SC0 is the 398.5 kilojoule. Hayes law, it states that the total enthalpy change during the chemical process is independent of the intermediate stages through which it may proceed and depends only on the chemical nature and the physical state of initial reactant and the final products. That is the Hayes law. Whatever the change in enthalpy is there during the chemical process is independent of the intermediate stages through which it may proceed and depends only on the chemical nature and the physical state of the initial reactant and the final product. That is very much important. This is the Hayes law. The MCQ will be there based on this particular Hayes law. Hayes law, what will be there? Hayes law proposes that or states that enthalpy change is of intermediate stages independent of the intermediate stages. Likewise, his law says that the change in enthalpy is depend only on that, like the MCQ will be there. Okay, very simple it is. Again, you can see so many steps are there here during the formation of this particular compound, but that depends That change in enthalpy depends upon the chemical nature and the physical state of the initial reactant and the final product. Okay, here that's shown. Then the bond energies, enthalpy of formation, that we have seen already. Enthalpy of atomization, the value of delta H for the reaction in which one mole of a compound splits completely into its component atom in the free gaseous state. It's called as the enthalpy of the atomization. It is denoted by the delta HA. Here the methane is there in the gaseous state, will convert into the carbon graphite along with the twice H2, that is the hydrogen gas. Their atomization enthalpy of the atomization will be the 1663.55 kilojoule per mole. Then the mean bond energy. The mean bond energy of the bond AB may be defined as the energy required to break AB bond in the molecule when all other bonds are broken at the same times. Okay. This there will be the MCQ based on this particular enthalpy of atomization and mean bond energy. Bond energy always positive because heat must be absorbed to break a bond. MCQ will be there. Bond energy is always dot 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 positive, negative, zero remains unchanged. Why it is? Because the heat must be absorbed to break the bond. It is denoted by the EAB. Delta HA is equal to summation EAB. Okay. Each bond breaking individual bond, energy required to break the individual bond. Okay, then you can take the mean, that is nothing but the you can sum all these things, it will give the delta HA. Okay, here where the methane is split into its component atom, all four of its CH bonds are broken, means you can write this particular energy for all the four bonds, means here 4 divided by 4 you will get the energy for the individual bond breaking for 15.88 per mole. Okay, here ethane is given, then the ethene is given and the ethine is given. You can see here how that particular bond breaking energy we have written. Then bond dissociation energy, that part we will see in the next lecture. Here we will stop. Thank you.